Welcome. My name is Brian Spiering. I'm a data engineering instructor at the Data Incubator. We're a fellowship, scholarship, and placement company. I promise y'all an excellent info session. I'm going to be leading it, and we'll be talking about navigating the landscape of machine learning operations. But first, to start off, I'm going to give you a little overview of what our programs entail. Then we'll talk a lot about machine learning operations. And at the end, we'll have some time for some Q&A. So a little bit of housekeeping. So today's session in total will be about 1 hour. The first 45 minutes will be me talking, and then we're going to have the last 15 minutes or so for questions and answers. Right now, all the participants are muted. That way I can answer as many questions as possible. I love answering questions, so we're going to have lots of time for that kind of great question and answer. Please submit all of those questions in the QA box. The chat will be reserved just for general announcements and sharing links. Don't put any questions there because I won't really see them. If you want me to answer any questions or have the admissions team answer any questions, they belong in the QA box. If you have any other questions that we don't kind of get to or outside of this session, feel free to email admissions at the Data Incubator. A recording of this session will be sent to all the registered attendees about 72 business hours after we conclude this session. So that's it for housekeeping. So let's talk a little bit about me. So I'm Brian. I'm a data engineering instructor here at the Data Incubator. I've studied psychology and neuroscience at the University of California, Santa Barbara. And through that process, I realized that I really just love coding. And so I actually spent more time writing statistical software than I did spend on my dissertation. And I spent more time like managing data infrastructure than doing the actual research. And I realized that, hey, that made a lot more sense for me to like work as a professional engineer, wide variety of things, data engineering, natural language processing, NLP. And I also love teaching. And in my spare time, I enjoy being outdoors, camping, rock climbing, playing guitar outside. So that's enough about me. Let's talk a little bit about the Data Incubator in general. So what we can see, we offer several different training programs. And what we have upcoming 2 data programs coming up. One is focused on data science, one focused on data engineering. I'm the primary instructor for the data engineering one. For the data science program, there's 2 variations. One is a full-time variation, and the other one is a part-time variation. One thing that's consistent about all of these programs is that they're intense. So the idea is that we get hands-on working through these data curriculums, and then we have a lot about like the knowledge that you need and the tooling. And we're going to give you a little flavor of what that looks like when I talk later about machine learning operations, so you get a sense of what it's like to be a student at the Data Incubator. They're thorough, so we really try to give you a complete overview of data science and data engineering for those respective curriculum. And we're really a big fan of active learning. So throughout the entire program, you'll be getting hands-on, working your way through that. It's also collaborative. So we have the students working together throughout that and receiving feedback from not only your peers, but instructors like me. And all of the programs are very career focused. So the goal is to give you the knowledge and skills that you need to get that data job. And we also provide support for that throughout the program, so you can look for that data-oriented job. And as it says on the screen, 88% of our graduates are working as data scientists or data engineers within 6 months of completing the program. So the way the program works is that for the full-time program, it's 8 weeks long. It runs Monday through Friday, 9 to 5. And then usually there's a little bit of a combination of lecture, there's some coding activities, and then office hours where you get to kind of ask questions and answer them, kind of very similar to kind of our Q&A style approach. And so all of this is expected about a 40+ hour commitment. Then we also have a part-time program for the data science program. Same exact content, only instead of being 8 weeks, that same content is stretched over 20 weeks. It's a little bit slower of a pace, but it's the same style. So it's live lectures with an instructor like me. It's hands-on activities, It's working through realistic projects through all of that. In particular, what we're interested in is this capstone project. So the capstone project is a project of your choosing that you want to explore. So maybe you have a data set that you're interested in, a certain problem that you want to solve. So what you do is you propose that, and then you get feedback from your peers and instructors like me. And throughout the course of the program, you develop this typically a working data application that demonstrates your data skills. And then along the way, we have a career services team that helps you improve your resume, hone your interviewing skills. And then we also have a partner network that we give you access to. So the details of how that program works is here. So you can see right here how the curriculum breaks down for the 8-week programs. So for the 8-week programs, we start out with the fundamentals for both of them around data wrangling, making sure that you're able to be fluent in understanding the fundamental tools in Python that are used in data science and data engineering. Then we focus on machine learning. So the core algorithms that you need to build and train machine learning models. And you can't do data without doing SQL. So SQL allows you to use databases. So we have a section on SQL. At week 4, the data science and data engineering curriculum split. The data science oriented curriculum focuses on visualization. So the ability to communicate those results that we got from the data wrangling and the SQL. And then it goes into more advanced machine learning. Then we have this thing called thinking beyond the data, and that's putting it in the context of a business. So can you actually solve a business problem with these skills that you're learning? Then we cover Spark. Spark is a distributed framework for ability to do these data-oriented tasks at scale. So when you have big data and it's coming in very, very quickly, Spark is the go-to tool for that. And lastly, we end on deep learning. Specifically the TensorFlow/Keras framework. So we give you those hands-on skills for contemporary deep learning. Jumping back over to the data engineering bootcamp, the first 3 weeks are the same. And then at week 4, we split over, and then we work on data in the cloud with Amazon Web Services. So that's data in the cloud. So once your data gets too big for your local computer, you get access to a whole bunch of computing in the cloud. Then we talk about Apache Airflow, which allows us to automate the workflows so we can move the data around and do what we need to do with that. And then we have distributed computing, so focused primarily on Spark. And then we lastly, the last 2 elements are around advanced processing in the cloud using Amazon Web Services or AWS Lambda service. And then this other one called EMR for batch processing. And then the last week is focused on streaming data. So sometimes the data just comes by as it comes by, for example, sensors. And so we talk about the most common ways of processing that using PySpark and Kafka. So that's kind of a quick overview of our curriculum. So let's move on to the talk. So that is what I'm most excited about. So this will give you a sample of what it's like to be a student at the Data Incubator. So here's my whiteboard. So today's talk is going to be about machine learning operations, MLOps, and MLflow. So we're going to talk a little bit about the kind of theory or what you need to know, and then what you can do with it. And so the MLOps part is the conceptual understanding of what we want to do. And then the MLflow part is a specific tooling. And I'm going to give a hands-on demo for that once I walk through this part. So what is this MLOps? Well, the M stands for machine learning, or ML. So machine learning. And then the ops stands for operations. And so when we talk about operations, what we're talking about right there is we're talking about software engineering, we're talking about production skills, we're talking about having this be in front of actual live users. So this is not machine learning at the theoretical level, this is machine learning at the very applied level. So the ability to actually get the value out of this machine learning. And what this does is actually come from actual pain points. So for example, last week, I was actually getting tea with a couple of people that are working on a website feature for predicting housing prices. And one of the people on the team is a data scientist. That person develops the model about predicting housing prices. And then the other person is a software engineer that's meant to put that model into production. And they really kind of speak a different language and they approach the problem a little bit differently. And so while I was chatting with them, they were saying the same ideas, just using different words. And the idea behind machine learning operations is to bring that together. So bring together that data scientist and that software engineer together to be able to deliver the value of that. And let's use the rigorous of software engineering to improve data science. So software engineering uses, version control, continuous integration, continuous development. They have a very mature way of approaching these things. Machine learning in general might be a little bit less mature. It's an ability to move that forward. And it's related to another concept called DevOps. And that was coming from the fact that oftentimes you develop software and the ability to develop that software is different than your ability to actually deliver that software. So what they did was try to combine those two together. So what they were thinking about was the ability to combine the ability to develop the software with the operations of the software for that. And this ends up being very, very different, very, very related to this notion of machine learning ops. And the idea is that traditional software, you get a specification for that software, you implement that software, you then test it, you send it out, and it just works pretty consistently. Machine learning is a little bit different in the sense that it's data-driven. And so once ever you have that data can change. And so as that data changes, the software needs to change. So that data ends up influencing it. And the data that you might have trained on might be different than the data that is later on in production. And we have to kind of handle that and work through that. And that's why it's really difficult to do that. And so there's kind of a subtle difference between writing software that goes into production and writing machine learning algorithms that go into production. So that's the kind of general overview of this. And what ends up happening with machine learning ops and DevOps is there's a series of platforms that allow us to kind of work through that. So give us these toolings that help us build the model, train the model, and deploy that model. So let's chat about that idea a little bit deeper. So what are the steps in MLOps? Well, the first thing, as I mentioned before, is we need to get that data. So we need to collect the data. And typically what we're going to do is collect data that's trying to be as realistic as possible. And oftentimes collecting the data takes the longest and is the most expensive step in working towards machine learning ops. And then once we have that data, we have to do the data science work of processing that data. We have to then distill that data, clean it. There's always missing values. We have to handle outliers, all of that to get it ready to then be applied for machine learning. Then we get the machine learning step right there. So that's where we're going to train and improve the models. And one thing that's a little bit different about machine learning operations versus other parts of data of machine learning is that we're really looking at the predictive value of this model. Can this model predict the data that we needed to do? And that's usually the number one criteria for this. There might be other criteria around bias, privacy, safety, reliability, robustness, but most of machine learning operations is really focused on the predictive ability of these models for that. Then once we have a model that we like, we're then going to deploy that model into production. So we're going to take that best model. Typically, it's an ensemble of models. And we're going to move that into production. So we're going to have the ability to then deliver that to end users. And that's a big step. So that's fundamentally different than just the work of a data scientist who's focused on, the best data, the best features, the best model. And then we need to move that forward. And then we need to think about working our way through that model. And it might be difficult to do, often is the case. Maybe the features that we trained on are productions, we have to modify that to make sure it works. Then the last step, which is oftentimes forgotten in this, is we need to monitor and improve the model. So once we put it in front of actual people, we need to make sure that it keeps working in the way that we expect it to work. So we have that model out there. We want to make sure that it's fast, it's giving the correct predictions. And then as the world changes, our model needs to change with the world. So here are the 5 main steps in machine learning operations. One thing to note about those is that they're all iterative. So oftentimes we don't just simply go from top to bottom in a straight line. Usually what ends up happening is we collect the data, we process it. Oh, then we realize we have to jump back, collect more data. We've done that. Then maybe we'll jump back to improve the models. Oh no, now we need more data again. And then we go through the whole cycle again. We deploy the model, we then monitor, realize it's not right, and we go back to the step again. So it ends up being a pretty kind of messy type of actual thing in practice, but these are the idealized steps with this. Okay, so that's the kind of general overview of what machine learning operations does. So the goal of this is to do all of this with an eye towards putting our models into production. And so then there's some tooling that's going to help us do that. We're going to focus on a single tool for today. That single tool for today is called MLflow. And the goal of that, as the name implies, is that we want the ML model to flow through those steps. So we want to have the ability to go through and train that. So what we have is this MLflow. It's a Python package. Machine learning tends to be dominated by the Python programming language. And that's why Python is the primary language that the data incubator teaches. And so we're going to have this Python package that's going to allow us to manage machine learning operations. And we're going to go through the ML lifecycle. So, we're going to think about that data coming in, typically say from a database, and then we're going to have that get prepped. Then we're going to have that training step. And that training step is typically a loop for that. And then here's what MLflow allows us to do. It allows us to then track this. So it ends up, this is tracking. So what we end up doing is tracking the training. And that's what we're going to be focused on today. So what we're going to focus on today for my demo that I'm going to start very soon is we're going to focus in on this step right here. We're going to focus in on the training and tracking step for today. And then if we have a little bit of time, I'm going to talk a little bit about what happens after you train the model, where you're then able to then, kind of select the best model and then deploy that best model. Oops, let me slide that up a little bit. So we're going to focus on that training and tracking step. So that's kind of the general overview of what the plan is for today. So let's jump into writing some code. So this is right here. So I'm in a Jupyter Notebook. Jupyter Notebook is the primary tool for data scientists and machine learning engineers for kind of working through and prototyping that. At the Data Navigator, we're going to be doing most of our stuff in a Jupyter Notebook. And so what a Jupyter Notebook allows me to do is have a little bit of text up here that tells us what we're doing, and then the ability to write some code. So let's kind of go through there. So the first step we're going to do is we're going to load the data. And what I'm going to do is reach into the most common machine learning library in Python called scikit-learn. And they have a series of data sets. So I can reach in there if I can type correctly. There's our data sets. And import that. And one of the things I'm going to import right here is this California housing. So I talked about, hey, these people were building these features to predict housing prices. So I'm going to show a little bit of a demo for like how they could approach that. So here's that. So now let's get our data. So here, fetch data. So one thing I like about this is that it's going to take me, a handful of lines of code to get our data, even though I had said previously that collect data step is the longest and most laborious process. I'm just kind of doing the short version of it. In a real data project, this would take far longer. So what we're going to do is we have this data right here, and we have two things in machine learning. We have the data itself, which we typically call X. So right here, this is the data itself. And that's just reaching into this thing called data and pulling out the data. And then we have the labels. And so the labels gives us what we're trying to predict. And in the case of housing prices, that's going to be the numerical value for that. And we call that data.target. So either target or label, those are kind of the synonyms for each other. So now we have the data itself, the features that we want to do, and then we have the ability to predict these California housing prices. The next thing we want to do is split the data into training and test sets. The idea behind this is training is going to allow us to then understand what features labeled X relate to the values in the target. And then once we learn that relationship, we're then going to see how good our relationship is on the test set. The test set is a placeholder for production data. So we don't have actual production data yet because we're just practicing and getting ready for our model, but this is the best practice. So we always want to have a separate training set and a separate test set. This is really important. Okay. For the sake of making me try to get to the good stuff, I'm going to go a little bit faster on this section. So again, scikit-learn, and then they have a function called train test split that takes in our features called X, our labels called Y, and then splits these into two groups. So you can notice we have X train and Y train. So those are the training features and the training labels. We also have the test features and the test labels. So this is the train test split. There it is. Okay, so now recall back from what I had just said, we have this data, we've done the train test split. What we need to do is define the models or the algorithms that we want to do. So for the sake of this, I'm going to pick two different models and compare them. So one model we're going to compare is going to be the one that's called the random forest. And these are both regressors in the sense that we have a continuous label for housing prices. So it's a regression problem. And we're going to use a random forest regressor and this other one that's called ridge. It's a linear model, which is also a regressor. It's kind of beyond the scope of this project to talk too much about these algorithms in great detail. The short story is these tend to be really, really common algorithms. They tend to be really, really powerful. And so they're good ones to start with. So now we have that notion of defining the models. Each of these models has knobs or ways of adjusting how the algorithm works. They're called hyperparameters. So what we want to do is define the possible hyperparameters that we need for this. And so what this is what are the possible knobs that we need to turn? So for this, we can see right here that when we have this ridge model, what we're going to do is we're going to do a thing called regularization. So regularization is the ability to penalize unnecessary complexity. So recall that we are up here with our train and test split. Sometimes we might be very good at memorizing the training set. Having this alpha or this regularization means that, hey, listen, we want to also have a lot of weight on our ability to perform on the test set too. So that's one common parameter for regression in general and ridge specifically. And then dropping down to random forest is a more complex algorithm. It has a lot more hyperparameters. A couple of these are just called number of estimators and maximum depth. I've set these right here. So what we did right here is say, hey, we have a set of algorithms. We have a set of possible options for these algorithms. What we're going to do is we're going to go and look at all of those combinations and see which one performs the best. So which one has the best ability to not only learn the training data set, but then to be able to actually predict on the test data set. So we're going to set that up and be able to work our way through the ability to search through that. And what we're going to do is a couple of machine learning fundamentals. One of that is called cross-validation. So what cross-validation says is, I have some data and I'm going to do a round robin around the data to figure out which of these possible values are better. Is alpha of 0 better than alpha of 1? And then it's going to compare those two. Or maybe we'll compare number of estimators 5 to number of estimators 10. So that's what cross-validation does. And then what we're going to do is we're going to kind of walk our way through that. And we call that grid searching. So if you've ever played the childhood game Battleship, where you shoot the little pins and try to find out where your enemy ships are, that's similar to what cross-validation does. It looks through and kind of finds out where things are. And what ends up happening is that this ends up being kind of complex. So we have a lot of different moving parts. And that's what MLflow is going to do. MLflow is going to help us keep track of what we need. Okay, so let's set that up. So as always with Python, we have a lot of imports to help us along the way. I'm just going to import these now, and I'll kind of walk through them as we set this up. So the first thing we're going to do is we're going to loop through this. So we've defined this thing called models with our algorithms and hyperparameters. We can then loop through that. So right here, we're just going to loop through that. So we're going to get the model name and the model info from these kind of parameters. And then this is where we actually get the machine learning MLflow code. So we go with MLflow .start, and we're going to start a run, and then as run. And so what a run is the ability to actually go through and actually train the model. So grab our data, grab our algorithms, grab our hyperparameters, and train that run. And then we can run a grid search cross-validation with that. So within this, we go into this grid search CV. CV is for cross-validation. We go grab that info for the model, and then we run this. So this is scikit-learn code. So this is the actual mechanism for training the model. But what's going to happen is, as that model is going to be trained, we're going to keep track of what we're going to do with MLflow. So what that would look like is this. So what we're going to do is we're going to go into MLflow and log what our model's doing. So we're going to loop through here and keep track of what we're going to do and what we're doing. In addition to doing that, we're also going to log more detailed information about that. So this is just general of like what's happening with our model and the options that we've selected. We're also going to keep track of what's happening. So what we're interested in is what is the best combination, which we call best estimator and scikit-learn for this. And then we're going to log that information to MLflow. In addition, as I said earlier, we're interested in the ability to predict on a test score. So not only do we want training to be high, we also want testing to be high. And so we want to do a really good job on both of those. And in this case, we're picking an error metric that is consistent with regression. And so it's called mean squared error. So what we're trying to do is minimize mean squared error. So the lower this score is, the better it is. So it's a little bit like the game of golf. So golf, you want the fewest number of strokes. When we're training regression on that, we want to minimize error. So what we're going to do is look for low test scores when we log it. Okay. Then the last thing we're going to do is we're going to print the results to the screen just to see what's happening. So that looks like this. So we're going to get the information that we want and print the results to the screen. And so let me run this code and you can see it and I'll explain it as it runs. So here we go. So this is what MLflow looks like. So we have this results for run.id. This is just a hash of what that run is doing. Under the hood, we can see right here that it's going to be a ridge regression. It's going to test the different values, alpha 0, alpha 1, and we can kind of see the results right here. So we can see that when alpha 1 is selected, the rank score is 1. So that's our best model so far. And then right here, this is our error right here. So this is our best run for this ridge regression. And then it does a different run. So we're able to then go to a different hash. And in this case, this is random forest regressor, and then looks at all the different possible elements of that. And then right here, it shows, hey, listen, this is our best result right here. So we can see that our last set of combinations is the number 1 combination. Go up here. So that means that, hey, we want max depth of 5 and then number of estimators to be 10. So what that ends up doing is sets us up for this notion of saying this, and then we're able to compare this. So remember, lower score is better. So we can compare random forest, the best model right here is there. Let's just look at these set of significant digits, 0.45, go back up here. Oh, that's better than 0.50. So right here, we have some evidence saying that random forest is a better model in this data set for this. And if you know anything about machine learning, that makes sense. In general, random forest tends to outperform linear models like ridge regression, but we just wanted to confirm that for this data set. And so what we have right here is we have the ability to then kind of set up and run complex models. Whoops, accidentally hid that. What we can do now is if we wanted to test other algorithms, we would just put these other algorithms in here. For this example, I just chose 2 to show 2 different ones. In most cases, I would probably try 5 or 6 different algorithms. And then within each of these algorithms, they all have their own hyperparameters. So in this case, I'm just showing a handful of hyperparameter options. In general, we would show maybe there might be 8 or so hyperparameters down here, and each of those would keep track of that. That's a lot. If you think about all of the different combinations of this, that's a lot. So different algorithms and different hyperparameters, and then within the hyperparameters, different values of those. That's a lot to keep track of, but that's why MLflow exists. MLflow exists to do the analysis and then also keep track of that analysis. So it's really helpful to manage that complexity of running these experiments. The cool thing is we don't need to just print it to the screen. I just printed this to the screen to kind of show you the kind of quick results. What ends up happening is that MLflow has a user interface called UI, and I have it up and running. So here's the user interface. So here's some stuff that I was doing yesterday right here. And then here are the ones that I ran today. So these are the 2 different runs that I ran today. So just for the sake of convenience, I'm going to get rid of the ones that I did yesterday and just focus on what I did today. So here are the 2 runs right here. What I'm going to do is I'm going to hide that a little bit, and we can look and see what the results are here. So what this does is say, hey, listen, I'm Brian. We ran an experiment. We kept track of when we ran the experiment, how we ran that experiment. And then in there, we can just add in a description or data sets. We didn't add those in yet, just for simplicity. But here's what's going on with this. So this first run is all the information that we have stored here. And the idea behind it is, if you've ever, right here, this is saved as output in the Jupyter Notebook cell. But if I run that again, what's going to happen is it's going to erase that. So say if I go up here and I like this result right here, I'm going to rerun the experiment, go up here, change this to 10, change this to 15. I'm going to change this one to 5, and then this one to 8. So I want to run a different experiment. So let's do that. So now we print out this result. It's going to take a little while to run. There it is. And so now we have another experiment that we try because we're just, trying different things. We jump over here to this. We now can see that it's been updated. And so now we could start comparing across experiments. So we can see right here, oh, here's random forest regressor with our different set of options. And then we can start comparing across experiments. And this is super convenient. So instead of just keeping track of it in my head, keeping track of it in a notebook, maybe using a spreadsheet, this will actually help me keep track of all the experiments that I've been doing throughout this entire time. And so this is going to make it a lot simpler to try all of the different various kind of combinations that we can for this, and then keep track of all of that. So let's kind of jump back in here. So we run these experiments. Say like I like this new experiment right here. Let's look at this. Yeah, random forest regressor. Here it is. There's our best one so far. And then we can kind of look at our metrics right here. And so we can see, oh, look at this. Our test score keeps going down, which is what we want. So it seems like we're on the right hunt. So it seems like we're going in that right direction with those parameters. So it seems like we need to keep running more experiments. So let's run in one more batch of experiments. In this case, I'm just going to get rid of this one. I don't think Ridge is going to help me in this case. So I'm going to go in here and just have this model. Seems like I'm going in the right direction. So let's keep going in that direction. I kind of like logarithmic spacing. So let's kind of make it a lot bigger. And let's see how that goes. We'll go here, we'll go 8, maybe 12, and maybe 20. So let's run that experiment. It'll take a little bit longer. The nice thing about this also is that since it saves it, if we lose our notebook, if we have, our kernel crashes or anything goes a little wonky with our Jupyter notebook, all that information is saved here in the separate machine learning MLflow interface. So maybe I hadn't thought about how long that hyperparameter search would take. So let's see, hopefully it runs fairly quickly, but if not, no big deal. That's the nature of machine learning training. Okay, while we're waiting for this to load, starting to go, it's still running. I see there's a question in the Q&A. I can get to that right now. Is there a target test score in general? So in general, yes. So in general, we're doing what's called supervised machine learning. So we're doing a thing where each item has a label, and we're seeing the delta between the predicted label and the exact label. So then we're going to look at the delta between those things. And we're going to try to minimize that delta and minimize that error. And what we want to do is minimize that error on the test set. So that's going to be what we call our North Star metric. That's the metric we're going to want to minimize. Okay, hopefully while I was chatting, it's still running. So we're still, I must have picked some other ones. But what we can do is we can see right here that we had the first set of experiments, and we can see the results of the first set of experiments. So let's take a quick peek at those and we'll keep going. So here's our random forest regressor. We jump down to test rank score. The last one seems to still be the better. And then right here, you can still see that our test score is still going down. So we still have a little bit of work to do for this. Okay, so that is kind of the brief overview of MLflow. So as we said right here, we're focused in on that training and tracking step. There's a lot of complexity to measure in that training and tracking step. One last thing I always do with every time I talk about any kind of tool is I talk about the limitations of this tool. So this tool is so useful for having us be able to track our experiments, but there's some things that are a little bit rough in that tool. Every tool has its limitations. Okay, so the number one limitation is that this tool is relatively new. So there's still some rough edges. I've actually using this tool to create this demo. I've actually found some bugs, and I was chatting with them on GitHub about kind of fixing some of their bugs. So there are some issues with using this tool, and so there's some like rough edges with using this. So be careful about that. Number two is that this might be too many features for a small projects. So it might do too much if you just have a very small project that you're looking to do. It's really designed for working machine learning engineers to manage the complexity of running multiple experiments, as we saw here. That experiment's going to take a bit of time. We're then going to have to, we might want to go do something else. And so as that experiment runs, we're going to keep track of that, and MLflow is very good for that. And then the last one is kind of the thing that kind of gets me, is that there's no tools, no support for collaboration. So right now you can kind of see me working as a solo developer doing this. And what ends up happening is that there's it doesn't allow you to actually kind of share results pretty easily with people or have a common workspace for doing this. Get that. So you might want to think about other tools if you have needs for collaboration, and MLflow doesn't quite work for that. Okay, while I was chatting, let's see what's happening over here. I think it's still running. So let me just refresh this and we'll see. I think I might have picked some hyperparameters that might take too long. Yeah, it's still running. So yeah, that's kind of the nature of doing machine learning training, is that sometimes it takes a little bit of time to do. We don't quite have the time in the demo to see the results, but we see the direction that we're trying to go in. So in summary, what I talked about was the ability to do machine learning operations. So we're thinking about taking that machine learning operations and moving it towards production. And we've seen people do this before. And the previous ways of approaching this have been called development operations, or DevOps. Machine learning ops is a cousin of that. And we're going to kind of take this data-driven approach of collecting data, processing the data, improving the models, and then deploying and monitoring that. And we can use tools like MLflow to help us. Okay, so that ends my part of the demo. So what's going to happen now is I'm going to turn it over to my colleague on emissions, who's going to cover a little bit about the emissions process. And then after that, with whatever remaining time we have, I'll try to answer as many questions as possible. Molly, are you ready to take over?
Yes, thank you. If you want to stop sharing your screen, I will go ahead and share my slides. Thank you. Okay, and can everyone see my screen?
All good.
Great, thank you. Let me just move things around here so I can actually see all my notes, since I have about 1 million different things open on my computer. Oops. Sorry, 1 second. Okay, perfect. So many of you have asked if we offer scholarships to any of our programs, and the answer is yes, we do. We admit 2 different types of students into our data science and data engineering programs. Fellows are offered tuition-free scholarships to our full-time program. We offer a limited number of these scholarships to highly qualified candidates. Fellows are expected to leave any current employment to attend our programs and are expected to interview exclusively within our hiring partner network. Scholars will pay tuition to participate in our program. They are not required to interview solely within our hiring partner network and may maintain current employment. Scholars still have access to all the same curriculum, resources, and tools as our fellow students. And the full tuition scholarships are not offered for the part-time program. We will be continuing to offer our Women of Excellence in STEM scholarship, as well as our Equity and Diversity in Data scholarship for our winter 2024 cohort. These scholarships aim to help improve barriers and provide opportunities for women, veterans, members of the LGBTQIA+ community, and students from racial and ethnic backgrounds that are traditionally underrepresented in technical roles. Our scholarship applications are open now. So if you go to the dataincubator.com/programs/scholarships, you can review the qualifications and apply today. A big component of our program that we pride ourselves on is helping our students not only grasp data science and data engineering concepts, but also help get placed in that field. For our data science fellowship program, 97% of our students that go through our program are currently employed outside of academia, and 88% of them are employed within 6 months of completing the program. That's part of the challenge, not only learning content, but being able to transition into data science or data engineering role. That's really where our program stands out because we help you with both of those things. So where are graduates working and what are they doing? Our graduates are working in 55 different industries. Some of the most common industries we see are computer software, internet, IT, financial services, and biotech. Some of the typical job titles we see are data scientist, data analyst, research scientist, data software developer, and product manager. These titles and roles vary depending on the company and the industry, but these are some of the roles we've placed in the past. Many, if not most, of our current hiring partners are also looking for data engineers. We've seen the demand for this role has grown 40% year over year. We've also seen our graduates earning 16% more than the industry standard, which is very exciting to see. Here's just a short list of some of our data science fellowship hiring partners. As I mentioned earlier, many of these companies are also hiring for data engineering roles as well. So we've also had people ask for if we have financial aid options, and the answer is also yes. In addition to our scholarships, we have partnered with LEAF to provide an income sharing agreement. You can participate in our program with just the deposit down, and you will not be required to make any payment until you've graduated and are working and earning more than $40,000 annually. We also have 2 different additional financing options that are all now available through LEAF: the tuition installment plan and the contingent payment plan. The tuition installment plan allows you to make fixed monthly payments over 12 months. And the contingent payment plan, you can also participate in the program with just the deposit down, and you won't be required to make any payment until you've graduated and are working and earning more than $50,000 annually. After that, you would be on fixed monthly payments for 24 months. We also provide loans through Ascent, and Ascent offers 3 different payment options. Deferred repayments, which is no payments until or no payments during the program and for 3 months after the program ends. Interest-only repayments, which are small interest-only payments during the program and for 3 months after, then full payments begin after that. And then immediate repayments. You begin making payments 1 month after the program begins, and they have either 36 or 60-month terms available. Lastly, for many of our part-time programs, companies are willing to sponsor or pay for their employees to go through our program. It's a win-win. You get to learn great stuff in the evening that you are then able to apply to your job during the day. If this is something that you think your company would be interested in or you would like to present to them, we do have a letter that we can provide you that will help lay out the program and the benefits of attending. And so where are we at right now? We do run multiple cohorts a year, and our fall cohort is starting in a few weeks, but the application for our winter 2024 cohort is now open. The winter full-time cohorts run from January 8th through March 1st, and then the part-time runs from January 8th through May 24th. The early application deadline is going to be September 29th, and then the challenge deadline will be October 2nd. The full-time cohorts are 8 weeks long, and the part-time cohorts are 20 weeks long. Some of the specifics about the application, we ask that you submit your application again by September 29th for the early admissions deadline. You'll then have 72 hours to complete the coding challenge from the time you open it, with the final challenge deadline being October 2nd. You cannot complete the challenge unless you've submitted an application. In general, we recommend you complete the application and challenge sooner rather than later to avoid any technical issues. and we are unable to reopen the application or challenge after the deadline has passed. And that is it for early admissions. We do also offer regular admissions after our early admission cycle ends. So what's the difference between these? We evaluate applicants on a first come, first served basis. So if you want to have a better chance of getting a fellow spot or being selected for a scholarship, or just knowing earlier if you've been accepted into our program to secure financing, I absolutely recommend applying during the early admissions cycle. We also offer a priority enrollment package for all of our programs that includes access to a Python training course, early access to career services, as well as $2,000 off of your tuition if you use the direct payment option. If you're interested in applying for a program, which I hope you are, you can go to thedataincubator.com/apply to submit your application. And if you have any questions about your specific situation, this presentation, or going through the application process, you can reach out to us at admissions@thedataincubator.com, and we'd be happy to answer your questions. And that is the end of my section. So I do see we have a few questions here.
Yes, thanks, Molly.
Yes,
Yeah,
I'll stop sharing my screen so we can properly see these.
Okay, great.
Okay, so the first question we have for Brian is, shouldn't it be theoretically possible to use AI to choose the likely models based on the data characteristics to find use case?
That is correct. So that's a separate field called auto ML, auto for automate machine learning. And that's machine learning on machine learning. And that's a really exciting field. It's a little bit immature to really use in this use case. So in this use case, we're really designed about trying to solve a specific problem and move that into production in the short term. In the future, yeah, auto ML is going to be really a very, very powerful tool, but it's not quite ready for getting things ready to like solve problems right now. In addition, as you noticed before, when I was doing the search, it took a lot of compute to do that search. And AutoML takes even more compute. So oftentimes you actually just run out of compute resources. And that's why we kind of need to scale things up for the cloud and the cluster. So AutoML increases the scale at which we do machine learning also. So again, not quite ready yet.
And it looks like there's a follow-up from that same person that says, furthermore, is it possible to automate the training/test/evaluation routines to find the optimal model and parameter?
Yep, that's the same thing. That's what AutoML tries to do. So AutoML says, hey, here's my North Star metric. Please go search that space for that North Star metric. What I was doing right there was the simplest version of that. We would call that cross-validation with grid search. So systematically searching through every possible value. There's a lot better ways of approaching it. Turns out random is actually a better way than grid searching. So instead of systematically going item by item, we just actually pick random places in there. And that turns out to be faster than systematically searching it. And then there's actually a set of algorithms that help us. So I love Bayesian statistics. So there's a thing called Bayesian optimization that allows us to build a model of what our hyperparameters look like and then search that space more elegantly. So those are all different options. I was just trying to show the simplest possible option, but there's a lot of different approaches towards that. And they fall in that umbrella of auto ML.
And then another question we have is, when you are testing various algorithms, can you set a target test score to benchmark how fast each algorithm is achieving minimal error?
That exactly. And that's what you oftentimes do as a working machine learning engineer. So when I worked as a machine learning engineer, we'd oftentimes not necessarily have to find the best model. What we would want to do is find the acceptable model. So we want a model that has certain performance characteristics, work with the product owners to find out what those characteristics are, and then find the simplest model that can meet those characteristics. And in science, we would call that Occam's razor. The simplest explanation that could fit the set of circumstances. In machine learning, let's do the same. And so instead of having unlimited complexity in a machine learning model, let's rein in that complexity. So we would do that. What I showed you was a bunch of Python code. Well, you could just write that in that Python code. So while I was searching there, I could say, if test score equals, say 0.25, stop searching. And so that's the advantage of having this all be exposed as Python code. You could just write Python code to find that dynamically.
And the last question we have in the Q&A for now says, does MLflow help narrow down the features? My impression from your demo is that MLflow is more on selecting algorithms/parameters.
Yeah, that's a great question. So the MLflow does a bunch of different things. What I was focusing on is one of the core things, which is selecting the algorithm and the hyperparameters. MLflow does a bunch of other things. It doesn't necessarily do that, what's called feature selection, because oftentimes that feature selection is built into the machine learning algorithm. So when I showed you that random forest regression was the best algorithm we found so far, one of the reasons why is that random forest automatically does feature selection as part of the learning process. So usually what happens in these kind of tree-based algorithms and deep learning-based algorithms, they do automatic feature selection within the machine learning algorithm itself. So the machine learning tracking tool doesn't have to handle that because the algorithm itself does feature selection.
And right now, there aren't any other questions in the Q&A. We have a few more minutes, so if you do have questions, be sure to enter them into the question and answer box so then we can answer those for you.
I saw a couple, since we have like a handful of minutes, I'm actually looking at the chat, so I'll just jump in and answer a couple of questions that are in the chat. Please post them in the Q&A just so we can keep track of them. But I'm happy to like do the ones that are also I see in the chat. Yeah, thanks for doing that, Alexander. What is the tool to track changes in the data and the effect on the model? That's the other core component is we're just tracking the algorithm. You could also track the data. The data tracking, there's a whole set of tools. One common tool is called DVC for data version control. And that would show if we started manipulating the data, getting new data, adding more rows, how is that all happening? And so you would have a separate workflow that would work on the data end of things. And then is LLM part of the program? It is. So we actually have seen the recent trend in large language models, in particular ChatGPT, and we've started integrating that into our curriculum, teaching you how to use the OpenAI API to like get access to those large language models.
I do want to chime in real quick as well. We are going to be releasing some courses in 2024 that will also touch a little bit on generative AI and LLMs along with NLP. So stay tuned. Anybody who registers for these webinars and is part of our newsletter will get an update about those courses when they are ready to launch. All right, it looks like we don't have any more questions coming in. I was gonna say, put them in the Q&A now or forever hold your peace. Otherwise, we will end the webinar and give everybody about 2 minutes back. All right, thank everybody for joining us, and we'll see you again next time.
Bye, everyone.